Yes. All right. Hello, everyone. Now, okay, finally we have everything up and running. I'm really excited for today's QuSCo on Air. We have Professor Klaus Mølmer here from Aarhus University. His expertise is in quantum optics, measurements, and quantum information with ultra-cooled atoms. He has also been very much involved in our work with quantum moves too. And so we've just sort of see each other in the university quite often. Fun fact is Jacob did his PhD under Professor Klaus, and I'm now doing my PhD under Jacob. So I'm really excited to have someone on QuSCo Air, to have that sort of line of PhD supervisors and students and so on. I would also like to mention, apart from Professor Klaus's academic work, he's also very well known for his outreach efforts. In fact, he's also written a book for high school students. And I would also like to mention that he's also leading the Gender Equality and Diversity Committee also in the department. So yes, Klaus, thank you so much for being here today, and I'm sure everyone is looking forward to this talk. And yes, and the floor is yours.
Thank you very much, and I apologize to everybody that I did not have the routine in Cisco. I'm a Zoom speaker myself, but now we will have I will say click every now and then, or shift, and then Shaima will change my slides. Now I was introduced as a grandfather, so thank you for that also. And it's, in fact, I will tell you a combination of new and old stuff. So the title of the talk is Precision Measurements, the noisier the better. And I'm going to talk about a special way to do precision measurements where we are observing the systems all the time. And when you're observing a quantum system all the time, then you have to deal with a continuous description of what measurements actually do to quantum systems. I know that you are in this quantum enhanced sensing via quantum control community, and there's definitely lots of possibilities to combine measurements and control. Just think about feedback strategies. And I think there's a big unexplored research area for how we can do the best possible measurements, the same way as there's a big research area for how to best control the evolution of quantum systems. But let's get going, so please switch to the next slide.
Yes.
Yes, so this is a Clint Eastwood from the movie The Good, the Bad, and the Ugly, but please switch again. So I will actually talk about the good, the better, and click once more. The best, or the theoretically best precision measurements we can do with quantum systems. So I will remind you what we try to do when we measure something with high precision using quantum systems. And then I will tell you about some of the challenges, but also possibilities that lie with this quantum metrology story. So please switch to the next slide. So of course, maybe you don't need to be told that, but there are many reasons to use quantum systems for metrology. So one thing is that they are microscopic, so you can do extreme near-field probing. What is shown in this picture is a small diamond, a nanodiamond with an impurity, could be an NV center, sitting right under the surface of this diamond. And if that's brought in contact with molecules, biological material, or whatever, then you are a very precise sensor to the distribution of spins and to the magnetic fields around spins in the molecular samples. So here you are just using the smallness, but of course, at the same time you get the smallness of your probe, you also get the quantum properties of the probe. So the probe is not a classical meter. It's, for example, a spin 1/2 or a spin 1 particle, and it's governed by the rules of quantum mechanics, particularly the rules of measurements in quantum mechanics, when you want to read out such a little meter. And if you switch again, please take the next picture on the slide. Then what is shown here is a patient in a hospital, and one wants to measure the magnetic fields from around the heart, the human heart, and that can be done with a small collection of atomic cells above the chest of this person. And of course, atoms are very sensitive to magnetic fields, so in this way you can detect currents inside the heart and do diagnostics. And there are different groups, also people we know from the quantum community, who are engaged with hospitals in making, for example, the diagnostics of heart of unborn children. So it's very exciting, and actually, of course, the kind of application I would be super proud of presenting out of my research. If you click again, and again, just twice, then I'm just listing that, of course, we have many other quantum systems. We have optomechanical devices that are very sensitive to acceleration and motion of objects. We have atomic clocks, which are also acting as inertial sensors, measuring retardation effects, relativistic effects. So all these quantum systems are very sensitive probes to very weak effects or effects that we want to measure with very high precision. So please move forward with the next slide. So what are the issues with quantum sensing? And if you have not followed this field, then I would recommend you to look into one of those two papers by Giovannetti, Lloyd, and Marcone on quantum metrology. So there's a Fischer letter and there's a Science article, which are about 15 years old. And there's a lot of issues related to quantum sensing that are actually described in those papers. They're super nice to read. So please click again. So the scenario is that you typically have a quantum system which is subject to a perturbation. So if we describe it by Hamiltonian, then there's a perturbation V inside that Hamiltonian. And that comes, of course, from the thing you want to measure. That could be a field, that could be a force, that could be an acceleration that manifests itself as a perturbation term in your Hamiltonian for the system. And due to that term, the state changes, right? And then after that, you have to do a measurement on the quantum system to reveal the change of state, and hence you can reveal also the strength of this interaction or perturbation V. And the questions you can now ask yourself, which are now coming on a small list, is, are there limits to this measurement precision set by quantum mechanics, by Heisenberg uncertainty relation? And if you click just a few times, then are there limits set by Born rule and the fact that outcomes are random? Are there limits set by the measurement back action, the fact that when you measure on a quantum, actually conditioned on what you measured the first time? And if you do measurements over time, is that going to give you a fundamentally different situation than if you prepare a quantum system, let it evolve by itself for a long time, and then measure at the very end? And I will have particularly this measurement over time as the theme in my talk. So there are many, many papers out there and many, many protocols actually that work by preparing a really good quantum state, subjecting it to an interaction. And when I said it's really good, it's because the interaction is changing it in a radical way, which is easy to witness. So if you, for example, displace the state of a harmonic oscillator by a small amount, you could use a squeezed initial state who has a more narrow distribution, because then it's more easy to see that it has been displaced. And then after that, you can then do the measurement, high precision measurement of how much it was shifted to see if there was such a displacement or not. But that's not the scheme I want to discuss. I'm actually going to look all the time at my quantum system, and this is really the main topic of this lecture. So let's please move to the next slide. So what I show you here is a funky quantum state. It's actually Markus Oberthaler who made an interesting state of a Bose-Einstein quantum set, which can be pictorially represented like this funny inverted letter S on a sphere in the left side of the picture. And now we can subject that quantum state to a Hamiltonian, and that Hamiltonian will then transform it into a different state, the state you see on the right. And I will distinguish in this whole presentation between two things. One thing that we call parameter estimation. So there's a parameter you want to know what is its precise value. So your Hamiltonian is function of some parameter. I call it theta. It could be a magnetic field strength. It could be a time retardation due to relativistic effects. It could be many different things. Let's just call it theta here. And then we have this other scenario of hypothesis testing, where you have a few discrete hypotheses, and you ask yourself, was the system subject to Hamiltonian H0 or was it subject to Hamiltonian H1? Okay. You can also imagine if I have hundreds of these hypotheses, then you put them on a grid, and then you can actually go continuously from hypothesis testing to parameter estimation, just finding the most likely value on a fine grid. If you do the parameter estimation, then you imagine that doing an experiment many, many times, you will be able to estimate the parameter theta. So it's all about making the estimation out of your classical data, which could be a histogram of measured values. You will infer what you think is the most likely value of theta. And what I show in the nice picture is how this funky quantum state leads to an outcome probability distribution of some measurements. This is the z coordinate. I'm asking where is the particle along the z direction. And if you do really many measurements, you will get a histogram. And that histogram of values is what you see as the blue histogram in the figure. That one is a random simulation, what you would get if you did a few hundred measurements. If you did another few hundred measurements, it would look slightly different. If you did millions and millions of experiments, it would look like a smooth distribution that I think you all agree we could calculate probably with quantum mechanical, with the knowledge of the wave function of the state of the system. So there is a prediction by quantum mechanics for probabilities, and then there's an experiment where you do a finite number of experiments, and then you want from that histogram to infer what's the most likely value. And anyone who ever took a lab course in physics knows that there's an error bar, and the error bar goes as 1 over the square root of the number of experiments you do. So we do expect from this situation that repeating this measurement n times, building the histogram of values, you can estimate the parameter with an error bar, which goes as some constant a divided by the square root of n. Now, if I have a hypothesis testing, then I don't quantify by an error bar, then I quantify how good I am by what's the probability that I make a wrong assignment. So please switch to the next thing here. So the error probability really is inferred from the distance between the different data distributions. So I mean, if you have a data distribution who's spot on my prediction from quantum mechanics, then I think that this matches this value precisely. But of course, there's a variation because it's stochastic what you get in measurements. It's random what you get in measurements. So please go to the next picture. So here's the histogram, and then just take one more click. So let's just imagine that the red and the green curve were quantum mechanical predictions for the distribution of data corresponding to two different values of my control parameter, and then I get the blue histogram. So which one of those two looks the most like my data, and what is the error bar associated with those two? And of course, it's a little bit of a difficult question, but I will try to walk you through it. Please let's have another click or two on the slide. So the parameter A, as I called it as the parameter in my error bar, that's related to something called the Fischer information. So the Fischer information is a statistical quantifier that actually only depends on how likely are the different outcomes. And if you know that distribution, then you also know how likely or unlikely is a particular outcome, the one you get in your experiment. And from that, you can actually infer the error bar. And the formula, I will not show you many formulas, and don't care so much about the detail of the formula, but the one I show you on the screen has the function L, and that's the likelihood. That's the probability to get the data record D conditioned on having a particular value of your parameter. And you want that to depend on the parameter theta, because otherwise you can't distinguish whether you had one or another value. So what is in this sum is the derivative of that distribution. Mathematically, we take the derivative, we actually take twice derivative of the logarithm of the probability. But clearly that quantity is a measure of how much your outcome data distribution depends on the parameter you want to sense. And that sensitivity is weighted with how likely the different data are. So that's the last factor. And then when you sum over all possible data, then you get this kind of average sensitivity that you would expect if you do this measurement many, many times. And that's actually the formula for the Fischer information. And 1 over the square root of that, that's what gives you the error bar. If you do many measurements, you are allowed to divide by square root of n, but the prefactor is this Fischer information. So please, let's have another click. So this is the classical Fischer information, and I call it classical because it relates the actual outcome data. I mean, there's nothing quantum in this box. There's the value of the perturbation, the strength of a magnetic field that you don't know, and then there's the genuine data you get in your experiment. And this is about how well you can infer theta from real data. And actually, the Fischer information formula is from 1927. So I wouldn't say it predates quantum mechanics, but it has absolutely nothing to do with quantum mechanics. So next slide, please. So let me introduce another object to you, which is the quantum Fischer information. So that now I'm not looking at measurement data, I'm looking at the state. So the state transformation that happened from the nice S to this distorted value or distorted distribution depends also on this parameter. So there's a wave function or maybe a density matrix that depends on the theta. And therefore, of course, as a quantum scientist or theorist, you may ask yourself, how well can I distinguish two different quantum states? How well can I distinguish psi0 and psi1 or rho 0 and rho 1, who are the states conditioned on that Hamiltonian? So let me have another click on the screen. So the error, Well, on the right, you see here the scalar product between two states, psi0 and psi1. And that's exactly the quantity who tells how well I can distinguish two wave functions. So if two wave functions are orthogonal to each other, you know they are perfectly distinguishable. I can just do a measurement, am I in one or the other one? And because they are orthogonal, there will be zero probability for one and one for the other if that's the case. So this is the estimation, or sorry, the testing case. What you see on the left is the wave function overlapped with its own derivative with respect to the parameter. So if you think about distinguishing two really nearby states because you want to know if the parameter theta has one value or the next nearby values, then you need exactly this expression to tell how that overlap between those state changes. So it's actually the same expression, the same idea, that you want two states to be distinguishable. And the question, how distinguishable, how much does your state change when you vary that parameter? So these quantities here will tell us how well I can distinguish the two quantum states. And let me just have one more click. So here is a pictorial picture of my psi0 and psi1. And if I give you two such states, which are at an angle to each other, what is the best strategy? Is it possible to know if you are in the red or the blue state, if they're not orthogonal? And the answer is actually no, it's not possible to know with certainty, but there's an error probability. And the larger the angle between the two, the smaller is that error probability. If you click just once, then you see that the best measurement you should do is actually measuring whether you are in one or the other of those two black states, chosen to be orthogonal, but also as close as possible to the red and the blue one. And what you do is, if you get this one more click, if you get the upper one, then you just say, my guess is red. And if you get the lower black, you say, my guess is blue. And that will minimize your error probability. So this is very well known in quantum information science. This is part of the security of cryptography schemes. But in sensing, this is actually also the hypothesis testing scheme, right? That you can use quantum states who are not necessarily fully orthogonal, but still to teach you something with high probability. So let's move forward. Next slide. The classical Fischer information is a lower limit to the error by a given measurement, while the quantum Fischer information is the information present in the quantum state. And that gives a lower limit to the error by any measurement, because we have not specified what measurement you should do. And please let me have another click. The question is, of course, is the quantum Fischer information exhausted by classical measurement at all? Or is it just an abstraction? That's this quantum sensitivity, but maybe you could never do an experiment. And the answer is that sometimes we can actually exhaust the quantum Fischer information. We can actually do an experiment where we measure exactly the same, that property who leads to this precision, and sometimes we cannot. So this picture shows a spin, and the spin is precessing around the vertical red arrow, which is the magnetic field that causes the precession to occur. And let's just imagine that we know there's a magnetic field along the vertical axis, but we want to measure its strength. So the strength is, of course, given by the precession frequency of the spin. So you want to be able to measure that. And the picture I show you is the classical picture of the spin. But if I get one click, then you have the same picture again, except that now it's the block vector. So it's a quantum mechanical state, which is mathematically described on the block sphere, and visually it just looks the same. It's the arrow in this picture has the same direction as the spin in the real space, but this arrow is a representation of the state of the quantum system. And the precession is in the lower picture reflecting how the quantum state is moving around in this Hilbert space, and being apart, two states apart in this picture are the ones who are the more distinguishable or less distinguishable. So if the B field causes a precession around the z-axis, then you should not take a vector which is partly parallel with the z-axis, because then it doesn't change during that precession. You should actually take your spin to point in the equatorial plane, because that gives the largest excursion and therefore also the largest sensitivity to the magnetic field. And when you come to which measurement you should do, you should also not measure the z component, which is random 50-50. If you sit on the equator, you should of course measure some direction in the equatorial plane, which has the maximum sensitivity to the precession. And that very intuitive measurement is actually, for a system like this one, exhausting the quantum Fischer information for this particular measurement. But it's not always the case that we can do that. So let's please jump to the next slide. So now I actually want to come to the real talk, because as I said in the beginning, I'm not going to prepare, evolve, and measure. I'm going to measure all the time. So the picture I showed you here with a system who is transformed under application of a Hamiltonian will be replaced by another picture that will appear on the screen now, please, where I have a quantum system that I'm probing. So imagine this little red cloud is a cloud of atoms, and the big fat red arrow is a laser beam that is traveling through the cloud. And then after that, it's being continuously probed. So I'm measuring as time progresses, what is the phase shift or what is the intensity of that light beam due to its continuous interaction for a long extended period of time with my quantum system. Okay, so there's no before and after, there's actually measurement going on all the time. And if you just take one more click on the screen, then you can see here a kind of artificial measurement record. So you see as time progresses, my data signal is going up and down, and I can look at that signal, and it's from that noisy signal that I want to infer what is the Hamiltonian or what is the property of the original atomic system. So let's just say that the atomic system was prepared in a spin polarized state. And let's assume that there was a magnetic field who causes a precession of that spin. And let's assume that the laser probing is sensitive to that precession, such that the signal that is drawn in as my data figure here is actually proportional to the magnetic field that I want to sense. But of course, there's noise. There's noise because of the counting noise. There's noise because I'm using an atomic probe who has a quantum mechanical uncertainty about the spin direction. But all in all, we expect maybe a proportionality between the signal you see here and the quantity you want to measure. So that means that I can look at this figure and maybe take some kind of average and say that's my value. It's proportional to the theta I want to measure. And you can also see that it fluctuates, but if I average over long enough time, the uncertainty about the value should also go down. And actually, one can often argue that that error goes down as 1 over the square root of the time that you use for your integration. You can roughly think of it as if the signal is independent in separate intervals of time, then the longer total time you use, the more intervals you measure. And if these are like independent measurements, then you get this square root of time scaling. So this is the situation we are in, but I want to be a little bit more precise than this roughly independent proportional to time, and actually tell you what is the best way to analyze such a measurement signal. So let's move forward with that, please. So I'm not going to use just the mean signal, but another click, and let's see what happens. I'm going to take the real fluctuating signal. I'm taking into account that I'm doing a measurement on a quantum system, and therefore there's a non-trivial back action. The quantum state changes due to my measurements. And there's going to be correlations between different measurements, exactly for that reason. Every time I get a click in my detector, I kick the system with some back action, and that will, of course, influence the future outcomes of measurements on the same system. And these correlations and this back action will at first sight look as a really bad thing because you keep disturbing your good little meter. But in fact, it will turn out, I will show you, that this is a super powerful way to extract much more information than you would have thought from the measurement records. So please, next slide. This is one of my favorite pictures. It's actually a picture that Wojciech Zurek made for a semi-popular article about measurement problems in quantum mechanics. So what you see is a fence, and behind the fence is the quantum world with the Schrödinger cats and wavy objects. And on our side of the fence, we are standing with our measurement apparatuses and, in fact, the whole lab equipment that we are using to do experiments. So when we do quantum mechanics, we use wave functions or density matrices, and they are really representing the microscopic world. So they are mathematical objects, but there is a quantum system who is represented by this quantum state. And with the red arrow laser beam, for example, I can influence the system. I can put a term in the Hamiltonian who will make the system evolve so that psi of t depends on the strength of the laser, the frequency of the laser. And I have this Hamiltonian, which contains all these parameters. There can be the quantities I know about, and there can also be quantities that I don't know about that I want to measure by this scheme. So I have my Hamiltonian, and there are some parameters, theta, that I don't know about. And then I get a signal, for example, the photon emission from these atoms. And they are random. So my yellow photodetector is sitting there clicking along every time there's a photon being detected. And now I want to see how much I can maximally learn about this unknown parameter theta. So let's just assume that I knew the value. So if I knew the value, I would know the Hamiltonian. And if I know the Hamiltonian, I know the time-dependent state, rho of theta. And if I know the state, I also know what's the probability for the next detector click, because Born's rule tells me what's the probability for the detector click, or for any other measurement I might like to do on the system. So there's a probability for the detector click or the detector outcome conditioned on the value of theta, simply given through the quantum mechanical probability distribution, right? So the state depends on theta. I don't know what is the right theta. So in fact, I have to calculate that state for all my candidate values. And then I'm sitting with all these different states, but for any given value of theta, I also know how likely is a particular measurement outcome. So let's have another click on the screen. So the measurement data reveal the unknown parameters in a qualitative sense, but in fact, they also do it in a quantitative sense. What I really want is the simple P of theta conditioned on D. I want to know what is the probability distribution for that variable that I want to measure, conditioned on the data that I have received in my detector. And that's not what I have. What I have is P of D conditioned on theta. I have Born's rule, but the way to convert the Born's rule into what I really want, I have to use what's called Bayes' rule. And I'll show Bayes' rule on the next slide. So let's just jump to that right away. So here you see Bayes. He was a reverend, a priest in England back in the 18th century. And he made this beautiful relation that you see on the screen. Let's read it from the inside and out. So in the middle of this equation, it says that you have two events, A and B, and the probability that both are true is on the left, it's the probability that A is true and that B is true conditioned on A being true. And on the right, it says that, of course, B has to be true if they should both be true. And then A should also be true, which happens with the conditional probability of P of A being true, given B is true. So I'm going to now, or Shema is going to click on the screen, and then the middle term will disappear. Oh, sorry. No, let me just remind myself of this too. Fine. In this talk, the B event is the unknown variable theta. Okay, so it can have different values. And the A event sitting up there is the data observed in an experiment. So what the equation says from left to right now is that the probability for theta to have some value times the probability that that measurement value was observed is actually the same as the probability for the data to occur given the value of the parameter theta times the probability that theta was true. So this is exactly the relationship I want between the right-hand side, which contains the Born rule, knowing the quantum state, and the left-hand side, which tells how likely is now the theta variable given my measurement outcome. So let me have just one click on the screen. So this is the initial distribution for this theta I didn't know. So let's just say that there are two possible values and they are both equally possible. So the probability for B being 0 or 1 is 50-50. And then I do a measurement. So let's have one more click. And then I get some outcome. And one outcome has a probability conditioned on B being 0. And it also has a certain probability given that B was 1. So what the equation says is that the one who has a larger outcome probability is multiplied by a bigger factor than the one who has a low outcome probability. Simply more likely to get the outcome with one B value, one theta value than with the other one. And when you see that outcome, then you are going to update your probabilities. So the product of those two factors is giving the new probability for theta, and it has been updated, it has been multiplied by a factor, and the more likely event also leads to multiplication by the larger factor. So, I mean, you may want to go through and read the Bayes rule and check that this is how it works, but it's actually a very simple rule to apply. It's a very intuitive rule to apply, but be careful because there are also beautiful paradoxes and probabilities. So you can also cheat people. But the law is actually finished now, because what you see on the left-hand side of the equation is nothing but the updated probability for theta being the true value, conditioned on the measurement outcome we got. So if you just give me one more click, then the P of A, that's the probability that you would get that outcome, but we actually know it was the outcome because we're doing the experiment. So A happened. So it doesn't matter what was the probability for that. Now it's a fact that A happened. And given that fact, the probability that theta has one or another value is given by exactly this expression. So please one more click. This is the new P of theta conditioned on the data. And the really cool thing is, if you give me one more click, then that probability is just a new PRB. And then I can do another measurement and another measurement and another measurement. Or I can sit in the lab and then I can, in every microsecond of my registering, I can talk, what did I measure in that microsecond, that microsecond, that microsecond. So then this becomes, in the limit, a continuous update rule, where the more likely values will accumulate probabilities, the less likely ones will lose the prior probability. And as time progresses, you will be more and more certain which one is the more likely value. Okay, so it's a little bit the same as if somebody gave me a false coin which has heads on both sides, or they gave me the fair coin which has 50-50, and then they let me throw the coin. And the first time I see tails, and then I say, okay, that could be the fair coin, but it could also be the other one, it's 50-50. But then if I keep getting tails, my probability will be climbing that this was probably an unfair coin. And it will exactly follow from this Born rule. Let me see the next slide and show you a quantum example. So here is a spin 1/2 particle. And if you were fast, you could see that it was vertical, and then Shaim had rotated it by a small angle. And when it has rotated, it's in a superposition of the up and down state. And depending on this Larmor frequency omega, it rotates more or less fast. And if you give me one more click, then let's do an experiment where I will measure the spin projection along the z-axis, and I will measure it with time intervals tau. So every tau, I will go in and do a projective measurement and ask, is the system spin up or spin down? So the probability that it's unchanged will, and therefore actually will go back to the initial spin up state, is just the first amplitude factor squared. So it's cosine squared omega tau. That's the probability to be spin up. And after having measured that, the system is spin up again. So let's see a measurement record. It's of course a stupid one, but I like the example. So what is shown here is the probability to be spin up as function of time. And you see that I start out with the spin up state, then the curve bends down because of this rotation with the cosine and sine function. But then at time tau, I do a measurement, and this measurement set your spin up. So it goes back to 1, and then time progresses. And then, of course, I just start over and over again on this cosine squared omega tau dependence, and I measure 5 times in a row, up, 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 but then I measure down. Okay, and that's, of course, also possible. And then for the next few measurements, the measurement keep confirming that you are spin down. So the whole record, you can actually see it right here. Now this is the measurement record, and then the quantum theorist who knows omega can also draw this underlying probability for being in the two different states. But now we come to the sensing part of it. So let me have another click. Just one. Yes. So the omega, well, okay, then I got 2, but that's also fine. so I want to know what is the most likely Rabi frequency or Larmor precession frequency here. Okay, so I get this measurement record that you can see on the screen, and now I offer you 3 candidate values. A value omega 0, which is the true one, but don't tell anybody. And then omega 0 divided by 2, and 3 times omega 0 divided by 2. Okay, so there's a choice between 3 different values of this omega. And what happens in the figure, according to the data, the exact data I just described to you, is that when you get the first click telling you that you have not rotated, that you are still spin up, then the lowest value of the Larmor precession frequency would really be the one who has the highest probability to yield that outcome. If omega was 0, there would be no rotation at all, and the measurement said there was no rotation at all. So what is happening when you get the first click event is actually that the orange curve is stepping up a little bit. And that's because it was more likely to get that outcome with a small Rabi frequency. The black curve stays almost constant, and the blue curve makes a step down. And that's because the black curve is right in between, and the blue curve was less likely. And that's how the probabilities go. And then I do the next measurement. And the next measurement is just the same story. The orange curve is the one who is mostly in agreement with being detected spin up. And when you actually see spin up, the orange probability is increasing. And that's Bayes' rule. Exactly this multiplication factor, who is higher for the orange, smaller for the blue, and in between for the black one. So you can see that those 4 or 5 initial clicks makes the orange curve increase dramatically, incrementally in every step. The black curve stays almost constant. The blue curve goes down, 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 being the less likely one. Now it's very interesting because then, of course, if this would continue, then at some point you would be convinced that the orange one was the true one. It would definitely be the one most compatible with you detecting no flips of the spin. But then we see a spin flip actually, and that detection of the spin flip is just turning everything upside down, because now the orange one was the least likely to leave that spin flip in your measurement record, and therefore there's a drop in the orange probability, while the blue one increases and the black one also increases a little bit. And you can see it goes on again. Now there's a sequence without flips. The orange one goes up. Every time that happens, the blue one goes down. But what happens ultimately is actually that the black one wins all the probability. And I've done nothing but what I just told you. I'm just multiplying these probability factors. The events who conspire to make one of these probabilities very small, that's something it remembers for a long time. So when the orange curve has been knocked down to have a very low value, even though the last 4 detection events confirmed very little rotation or no rotation at all, the orange curve actually stays at the bottom at the end of the graph, and the black one, who has already gained almost unit probability, is not very unaffected at all by this particular detection sequence. So this is really how the Bayes rule works in conjunction with the Born rule, namely these outcome probabilities. So sorry, I saw on the chat that somebody asked if you can ask questions. Please feel free to interrupt me and ask questions all the time. Unmute yourself and interrupt me.
Can you hear me?
I can barely hear you. Just try again.
Yeah.
Yeah.
Okay, does that work better?
Much better, yes, thank you.
Yes, I wanted to ask, so does the continuous equivalent of this also work? Because here I can see that the probabilities start at 33. So there's equal probability of each of these Rabi frequencies.
Yes,
And
I'll show you an example next where everything gets more continuous than in this particular example. And,
okay.
And we also have special versions. Of course, you might say, if I want to put things on a computer and I have a continuous variable, then either I have to discretize it or I have to have an ansatz that the state is Gaussian or follows some other functional form. And this is exactly what we do for those cases. But I'll show you an example actually of both on the next slide.
Okay, thank you.
So let's just move forward with the next slide. So here's the one where we don't discretize time at all. So this is very familiar physical problem. I described to you here a 2-level atom, which I'm driving with a laser field, but the atom can also emit photons by spontaneous emission. So you can have a superposition state of the atom being in the ground and excited state shown in the upper left. And then in the next little time interval, there's a small probability amplitude for jumping to the ground state and emitting a photon. But there's a much larger probability amplitude that you are actually still in a superposition state of the two states. And if I'm doing master equation description of spontaneous decay, then I have to incoherently add those two components. And then you get the exponential decay of the excited state, you get the damping terms in the master equation. But what we want to talk about now is somebody sitting with an ideal perfect detector and waiting to see if these photons are actually emitted or not. So if the emission is instead detected, I have to project the state on the right-hand side. And if I see no photon in my detection, I have to project the state on the left part of that picture you see on the screen in front of you, the 0 photon component or the 1 photon component of this joint state of the emitter and the radiation field. So if you give me one more click, then you will see one of my favorite figures. It's an article I wrote 30 years ago, where I show a simulated trajectory. So what you see in the left is the atomic excited state population go up and down in what we call Rabi oscillations. And then we are constantly asking, did you see a photon? Did you see a photon? And as long as that curve is smooth, we didn't see a photon. But as soon as you see this vertical drop with a dashed line, that's because we saw a photon. So it goes down to the ground state because the state of the atom accompanying the photon being emitted is the atomic ground state. So the oscillations start over again at time 1.6 in this figure. Then you start oscillating until around 3.1, 3.2, where a new jump takes you to the ground state and the oscillation starts over again. Those of you who have known and solved the Rabi oscillation problem with master equations will be happy to see on the right-hand side of the figure that if I average over 100 of these trajectories, then I get the damped Rabi oscillations. So that's an average theory. That's what we obtain with density matrices. But if you observe the quantum system, then you have the situation on the left. I'm not here saying that I only measure those times where the clicks occur. I'm actually measuring all the time. This is what we call continuous measurement. But the outcome of the measurement is just 0 all the time, except those discrete click events that are shown here with the vertical drops. And this is where your detector says click, and you might hear it, or you see some bright spot somewhere in your laboratory. So let's and this is really a physical system. This is not a toy model constructed. You could have such an emitter, and you could use that emitter to try to probe, for example, the strength of the laser field driving this atomic transition. So let's just move to the next slide. Because here is a toy model. This is, of course, I'm a theorist. This is my blackboard. So I just remind myself that the model is a two-level atom. There's a Rabi frequency causing transitions up and down. There might be a detuning. My laser may be on resonance or not. And then there's a decay rate. So if you are in the excited state, the decay occurs with a rate gamma. And the click record is a random realization of the click record. So that's the red stars you see along my timeline in the top figure. That would be what such a record would look like. Let me see one more figure. The figure I show you here is the conditional atomic state driving the atom up and down as function of time, assuming a definite value of the Rabi frequency, which is exactly what governs this frequency you see in the plot, and then having the jump, for example, just after time equal to 5, there's a jump to the ground state. And just between 10 and 15, you can see 2 jumps also in the figure. So this is what the atom is doing if you're driven by that Rabi frequency and if you jump at exactly those times. Now, if I get another figure and another one, then you will see what the atom was doing if it was driven by a weaker Rabi frequency or a stronger Rabi frequency. So again, you're going up and down, but now at a slower pace, but the jumps occur at the same time. Right after 5, between 10 and 15, there are 2 jumps, and right after 15, another one again. So looking at the system and thinking that you're driven by the blue Rabi frequency, you think the atom is following the middle trajectory. If you think it's driven by the black trajectory, then you see these clicks, then that's your picture of what is going on in the quantum system. And if you think you're driven by the high Rabi frequency, then you think it's going up and down like the red curve. So let me have one click on the screen again. So here I've aligned those 3 figures under each other, and the vertical lines show you where the clicks occurred. And now I want Shaima to press on this just once on the PowerPoint. So what you see with these little stars is where the clicks occurred. But the stars show something more. It actually shows how excited the atom was given the black Rabi frequency, the blue Rabi frequency, and the red one. And the reason I show that height is that the probability for the click to occur is always the excited state probability. So it's actually more likely for the black realization to have a click at that time than the blue one, because you are 65% excited in the upper figure, but you are only like 15% excited in the middle figure. And in the lower figure, you're also about 60% excited. So if you got only that single click, you would find blue, the middle Rabi frequency, less likely than the black and the red one, right? And then let's just click once more, because now you can see what was the excitation probability for the subsequent clicks. And what you should do in Bayes' rule is you should actually take the initial probability assigned to those 3 cases, and then you should multiply them by the height at which these stars are sitting. So every time you get a click, you should multiply by the corresponding height. So you can see in the upper figure, you multiply by 0.65, by 0.9, 0.7, and then 0.25 or something like that. And in the other figures, you're also multiplying in the middle figure by something which is always small. And that means that's probably going to be ruled out by this measurement. But also the lower one has a few very small probabilities, so that's also going to be ruled out. So the conclusion is by one more click that yes, that this is the most likely one. It's a little bit odd. I would have liked to do that click myself, but that's fine. So and it's super powerful because you multiply a few numbers, and even if the probabilities do not seem to be super different, just the fact that you are larger or on average larger means that after 5, 6, 8 clicks, you have significantly suppressed the less likely outcome or the less likely hypothesis compared to the more likely ones. So let me show you the next screen. Here,
Klaus, I'll just interrupt you for a second. Yeah, I think someone just wrote to me that there's an option where you can ask for control of your screen, so you can change your slides. Yeah, just in case that would be more convenient.
How do I ask to control my screen?
So I think it's on the left. Since I'm on screen sharing mode, I think I don't see it. But maybe it's on your left.
I have mute, I have stop video, I have share, but then of course also in the upper left I have something called settings.
Settings.
That's not the one. That's not the one.
Okay, maybe I'll just ask Amit, who wrote to me. Amit.
Actually, it's on the left side of the screen. If you just hover around the screen, hover on the presentation, there are like
Yeah.
four tabs. So like the second option is ask to control.
I see not on the left. I see only in the bottom of the screen 3 dots. Then I have switch audio, connect to video, raise hand.
No, if you hover your mouse around the over the presentation.
I don't see anything happening. I'm sorry.
Okay.
Yeah.
Klaus,
Yes.
to right click on the screen.
I get it also from right clicking. Okay, so if I do right click, I can do view image, save image, select all this frame.
To get ask to control.
No, I don't have such a on the
It's
presentation.
also different, but I have on the
I'm
bottom
clicking on the presentation. I see nothing.
start video and share, and under share I can select screen.
We tried that. Should I try that again, Shaima? Because we did that quite a few times before we all turned in, and it just went bananas on my screen. It's not going to be the rest of the day, right? So I think
yeah, no, it's fine. I thought if it was more convenient for you, and I was also like, okay, one click or an accidentally, like 2 clicks would happen by accident. So, so I thought if this, okay, but I guess let's continue. Let's continue this way.
Alternatively, I could put on my mask and then I could run down to Shaima, who is actually just sitting 50 meters away.
Yeah, actually, that could also be an option. I leave it up to you.
Let's see. What do you think? Let's take, everybody can get a cup of coffee and I will turn up in your office, right? So where's your office? Where's your office?
Mine is on the second floor, 216.
Yes, super. I'll see you in a little while.
Okay.
You're muted at the moment.
Perfect. Thank you very much. My apologies for this little interruption, but I'm sure you all enjoyed the break from my voice. What I just walked through was this story about our detection. And just see if I can go. Can I navigate in the slides? Okay, maybe. So Shane, how do I? Is that page up and down? No.
So I just.
I should have to.
Yeah, this is.
Okay.
Yeah.
So good. Thank you very much. So as I told you, there are going to be these click events, and it's very important here. It's not the number of clicks that matters. It's actually not even the precise time where they occur. It's the time intervals.
Klaus, may I interrupt you?
Yeah.
Of course, we are not seeing the slide shared.
Okay, and then she just left. We're not seeing the slide. Mm-hmm.
It's fine now, right?
Yes. Now
yes. Okay.
Good. So, okay, we're having fun today. That's very good. Let's blame it on Corona. So what I showed you here was, of course, the detection record is going to be discrete click events. It's not the precise time of the individual events that tell us anything here. It's also not the number of clicks that tell us very much here. It's actually the time intervals between two consecutive clicks that tell us everything. Because the fact that you jump to the ground state in one click resets the clock. That puts your atom in the ground state. So instead of looking at those damned Rabi oscillations, who tend to forget their past, every time you see a click, you start a clock over again, you start full contrast Rabi oscillations, and you can see that going to the ground state around time 5 sets oscillations into operation, and then you will get your next click when the atom is most likely excited again, conditioned on being in the ground state at that time. And the only information in the figure is actually the distances between the clicks. That duration, because after every click, you again go back to the same initial ground state. So the measurement record could be just down to a histogram of how long time did you wait between consecutive clicks. The order doesn't matter, it's only the distribution. So here on the next slide, I show you the theoretical probability distribution for those intervals. So you see the red curve is oscillating up and down, and that's reflecting exactly that after a click, you have to wait till the atom gets excited. It's most likely that it happens in the first round, but if not, it will happen in the next round or next round or next round. And the blue curve is a fitted histogram, or actually it is a histogram showing the actual distribution of click events. And they follow very closely this red curve, as we would exactly expect. But you don't need thousands or hundreds even of clicks to make a very precise estimate of the Rabi frequency. The Fischer information that I talked about before can be calculated now, not by simulations, but actually just judging from random data picked according to the red distribution, how close will you be able to fit which red curve is the one closest to the blue data. So we can actually here calculate analytically the Fischer information. And it's very interesting because that Fischer information is independent of the Rabi frequency itself. It means that we are equally good at sensing between two low values of the Rabi frequency as between two high values of the Rabi frequency. And that's maybe a little bit surprising for a standard analysis, but not for this kind of analysis. And I'll show you why you should be surprised and then not surprised afterwards. So this Fischer information, this complicated expression, can actually easily be calculated analytically. Now, it's also easy to show that the Fischer information grows linearly with time. So this story about getting more and more information, the longer you integrate, getting an error bar that goes as 1 over square root of time, that's also coming out of this analysis. So there's a very steep learning curve for what is the value of the Rabi frequency. So now I do this base analysis for you, but with more than 3 candidates and with a real simulated record. So here is the conditional excited state probability, conditioned on clicks, and I think you can see where the clicks occur. Every time you have a full contrast going up to maximum value, it's because it's just after a click. So here there's about 40 clicks taking place. A normal steady state analysis would say that on average you would be so and so excited. And what is shown on the right is how the steady state population in the excited state varies with Rabi frequency. So in the beginning it grows fast, but then it actually saturates at 50%. So because any strong power will just saturate the system and put it with equal probability in ground and excited state. So it's very difficult to see from the accumulated intensity of fluorescence whether the Rabi frequency is high or very high, because it actually leads to the same signal. If you have an error bar on the detector count signal corresponding to the height of this green box, you really wouldn't know if the Rabi frequency is 2 or anything bigger than 2. But when we do the simulation, then what is shown here in a color scale is the most likely Rabi frequency as function of time. So you can see that initially it's all blue, and that means that they are all equally likely. But after a very short time, I have singled out some particular areas around 5 or 6 and around 2 or 3. And if I go up to the time around 50 here, where about 12 photons have been detected, the Rabi frequency is already narrowed in to a quite narrow interval. So this is really based on these intervals. They are really ruling out very quickly the unlikely or or even impossible values of the Rabi frequency. So this is the base rule, click by click, super easy to code and super easy to actually run for even more complicated systems where you're doing more complicated measurements. As long as you can evolve your condition state and you can calculate measurement outcome probabilities, you can apply this rule. And of course, you have to hope that these statistics in these measurement records depend on the parameter you want to judge or sense. But if that's the case, then you will get pictures like the one I show you here. I just remind you that 12 clicks for a normal experiment would mean 12 plus minus square root of 12. So that would be somewhere between 9 and 15 clicks, and that would not tell you the Rabi frequency with any good precision, and certainly not a value of the Rabi frequency around 3, which is well inside my green box in the right figure. So can we do the same with Homodyne detection? It's just another way to look at light from an atom. If you mix the light with a strong laser field, you're doing field amplitude measurements. And these are super noisy measurements because there's a lot of counting noise due to the strong laser field. But even despite that strong counting noise, if you integrate over time, you will still accumulate knowledge about the parameter you're looking for. So again, we didn't have the imagination to look for anything else but Rabi frequencies. So here we have an experiment where we are doing Homodyne detection, and I can see as function of time how I know better and better the value of that Rabi frequency. In this case, I chose a phase of my local oscillator. So I'm actually measuring a particular phase component of the emitted field from the atom. If I take another phase of the local oscillator, I'm not as sensitive. And that's exactly because the information sits in a particular field quadrature and not the other one. You still learn something, as you can see, but there's a better measurement and there's a worse measurement in this particular case. In this case, it's highly non-trivial to actually tell what is the Fischer information, and it's highly non-trivial to even make a kind of theory, how should you filter and precisely analyze the measurement signal. But Bayes' rule doesn't care. You don't have to be smart. You just have to discretize your omega grid, and then you just have to solve in parallel 50 versions of the same master equation, and then you will automatically get this very pretty convergence towards the best you can get out of your data. Now, I want to step up to something complicated, and that is how to calculate the quantum Fischer information. I hope I will not make it too technical here in the talk, but I just want you to get a flavor of how this quantum Fischer information, what it represents, and how we might even assess the value of it. And so what I show you here is actually the hypothesis testing version. So the upper part of the figure shows an emitter on the left, subject to a Hamiltonian H0, which causes it to emit radiation into the environment. So that's all the red waves propagating away from the system. But we don't know if it's the upper situation with H0 or it's the lower situation with H1. That's the actual case in this experiment. So how do we make the difference? So I just showed you that the emitted signal can actually make the difference. So the counting signal or the Homodyne detection of the red light propagating away will tell us ultimately whether we are described by H0 or H1. But now I want the quantum Fischer information. So in fact, I want to describe the upper part of the figure with one big quantum state, the quantum state of light and the emitter. And the lower picture is another quantum state of the same system, the quantized radiation field and the emitter. And I want to distinguish those two global quantum states. If you imagine this is a signal record of 1 second, then this state will fill the space from here almost to the blue. And those two states, shown here with the red and the blue, if there's an angle between them, then I can separate them. And of course, there will be an angle between them because those states will be different quantum states if the system has evolved for some time under different intervals. So I have to go through this exercise, but before I go through that exercise, of course, I have to admit I have no clue what are these wave functions. Nobody has actually ever written down the joint quantum state of the radiation field of an atom driven by a laser for long enough time that it has emitted lots of photons, because it lives in a huge Hilbert space and nobody can really calculate that state. So the minimum error for the quantum Fischer information here depends on the overlap between those two states. What is that overlap? And in fact, we can calculate that overlap even without calculating the state. And I want to show you why, because I think that's a fun component in this story about sensing. So what is the most we can learn by observing radiation emitted by a quantum system? And we have 2 papers in my group 5-6 years ago with students on Gammelmark. The first one here is the Fischer information, the quantum Kramer-Rao bound or sensitivity limit of continuous measurement. So in that paper, we really sense the precise value of a parameter and we find the limit of sensitivity. And that's technical in its own way. And what I will show you now is an easier version, namely the hypothesis testing, how to distinguish only 2 values. And I will make a comment on how that's related to the more general problem or the more difficult problem. So I just remind you again, there's a big quantum state of the system, the quantized radiation field. Nobody can calculate that state. So calculating the overlap between 2 such states is, of course, out of the question. But there's a nice trick we can do. I call it the quantum information wave. So let's assume that we have an ancillary qubit, and the qubit is in a superposition state of 0 and 1, and the qubit controls the Hamiltonian. So if you have qubit state 0, you have Hamiltonian H0, and if you have qubit state 1, you have the Hamiltonian H1. So it's like a controlled gate that's going on here. Then the initial state will evolve into a superposition state of 0 with psi 0 and 1 with psi 1. So I don't know what is psi 0, I don't know what is psi 1, but I know that if I start with the superposition state of 0 and 1, then that's the superposition state I will have after that interaction has been on for some time. And the scalar product between psi 0 and psi 1 actually plays the role of decoherence, because 0 and 1 were created in a superposition state, but because they are entangled with the system and the environment, then the psi 0 and psi 1, as they propagate away from each other, they actually kill the coherence between the 0 and the 1 component of the ancillar qubit. The mean value of the lowering operator of the ancillar qubit is exactly the psi 0, psi 1 scalar product here. Right? So if psi 0 and psi 1 are the same state, then your 0 and 1 will still be in a perfect superposition, and that lowering operator will be 1. But if you have any degradation due to the fact that you have sort of left an imprint in the environment of which ancillar state you were in, then you will lose that contrast. So I actually have rephrased this scalar product into being the decoherence of an ancillar qubit. And that is maybe not enough to make it easy to calculate, but in fact, for this particular situation, it is, because the ancillar plus my little emitter is a small enough quantum system that I can solve the master equation for that system. This is a system who is coupled to a big environment, emission of photons. We know that we can describe that by a master equation, a density matrix. So if I calculate the density matrix for everything inside this blue ellipse, the small system and the ancillar, then I can also calculate the mean value of the sigma minus on the ancillar, and therefore I also know what is this scalar. So I was very happy when I got that idea, I have to admit that. But well, we have happy days. That's good. So it's a density matrix equation I have to solve. So here is my block density matrix, rho 0, 0. That's the density matrix of the system, where the qubit ancillar is in 0 state. The rho 1, 1, that's the system density matrix, together with the qubit being in the 1 state. And then these off-diagonal terms, rho 1, 0 and 0, 1, these are the ones corresponding to the coherences of the qubit. And I have this big block diagonal or block form density matrix of the product state of the two systems, the tensor product, and I just have to solve for that density matrix. In fact, I don't even have to solve everything. I only need the rho 0, 1. And now I'll show you what happens. What is the master equation for rho 0, 1? The trace of rho 0, 1 is this overlap I'm looking for. So that's actually the whole quantity I'm going for. So now I just need to solve the equation to find that little block rho 0. And it solves a beautiful equation because it solves a master equation. But the fact that you have 0 for the ancillar and 1 for the ancillar has the consequence that the Hamiltonian acting on the left is H0 and the Hamiltonian acting on the right is H1. This is already not the Schrödinger equation because you use different Hamiltonians on the left and the right side of the density matrix. This is already causing a loss of trace, and this is already causing the distinguishability of the system to this effect. But then there's also damping terms, and if you are familiar with master equations, you know they look like this, but there's something new here, because every time I act on the left with my Lindblad operators, it's the 0 Lindblad operators, and every time I act on the right, it's the 1 Lindblad operators. So if the hypothesis is about different damping rates or about different terms in the master equation, then the terms corresponding to hypothesis 0 always act on the left on your density matrix, and the one to the hypothesis 2 always act on the right. If I solve this little master equation you see here, and I take the trace of the density matrix that I get here, then I have my overlap between my two states, and that's the one who tells me how well I can actually distinguish between the two. And this is quantum Fischer, so it doesn't tell me how to do it. It just tells me this is the best you could ever dream about, distinguishing those two states. So that's the gold stamp. This is what we might be the best measurement in the world on this radiation field. And the only thing that happens if you want to do sensing instead of hypothesis testing, if you want to go to the other paper with CERN, then you have to not put the two different candidate Hamiltonians on the left and right, but you have to put all the purple terms, while in the orange terms on the left, you put the derivatives with respect to the parameter theta. And then you get your sensitivity to the theta parameter. So it's, again, the simple structure of the master equation, but it's a little different because it's acted on differently from the left and right, but it will tell you at the end what is the sensitivity to this or that parameter. So a very simple illustration here is if I have a two-level atom driven and it can decay, what's the probability that I can judge after some time correctly if it's driven by a laser or not? Okay, so imagine that you see no photons. Of course, in the beginning, it could be just because you didn't see one, but after a long time, you would probably conclude it's because I'm not driving it, I'm not exciting it at all. But there's an error probability with that goes to 0 with long times. And if you look at the blue curve here, this shows the error probability. I mean, if you're guessing the field is on, the field is off, then on average you would guess wrong with a probability given by the blue curve if the information you have is the photon count. Okay. If you have both photon counts and you can do a projective measurement on the atomic state, then you can actually go a little bit lower or quite a bit lower, shown by the red curve. And the black curve I show you here is a quantum Fischer. So I don't know how to reach the quantum Fischer at those intermediate times, but there is actually a potentially in that complicated state of the field in the atom, a distinguishability of those candidate states that is better than what you get by just counting the photons and measuring the atom. The state is an entangled state, and in that entangled state, there might be other degrees of freedom that you should have measured rather than just the number of photons or the excitation of the atom. So it's a kind of funny, and it's always fun to compare quantum with classical physics. So this is what we do here. We can also do multiple hypotheses. This is actually a simple extension. So you can ask, which of 4 states do I have? Which of 8 states do I have? Which of 4 Hamiltonians do I have? Which of 8 Hamiltonians do I have? And it works. It's of course more complex, but it's fun that we can also do that, and potentially also very interesting. With another student, Alexander, we have this multi-state, multi-hypothesis discrimination with open quantum systems. And we have the second paper, and you think it's the same hypothesis testing, but the upper one is the quantum Fischer. That's the one where we just ask fundamentally how much is actually known, could be known by the quantum state of that system. While the lower case is actually true monitoring. So this is the classical Fischer. And as I said before, it's always great fun to compare the two to see if you can actually exhaust the quantum. Sometimes we can, sometimes we cannot. Now, I'm nearing the end of the talk. I also apologize for this disturbance in the beginning, but I'd like to show you just 2 practical analyses we did, where we're not talking so much about limits, but more about what do we do to actually get the most information out of it. So the physical setup we have here is one to measure magnetic fields using atomic ensembles. So there's a lot of atoms, the green dots, but in reality, maybe billions of them in a glass cell. And you have optically pumped them to make them all put in a particular spin state, and then you put on a magnetic field that causes the spin to precess. Okay, and then using the red laser probe, you can measure that precession take place. So what you do is you measure the polarization of the field by a counting measurement. You split polarization components and measure the difference in counts. And that tells you how much your probe was rotated. Eventually, it tells you how much the spin had been rotated, and therefore it also tells you how strong was the magnetic field. So that's really what this experiment is about. And people who do that on the Danish scale is Eugene Holzig in Copenhagen. Jakob has been involved in that kind of experiments too, and some of Eugene's other former students are sitting around in the world doing this kind of experiments. What I show you here on the left is the true magnetic field in green. True for a theorist because I have simulated it. So it's just the value that I use to drive the spins. And then I do the dynamics of these atoms. And I had the question before about continuous variables. Here I have millions and millions of atoms, but they are actually described by a Gaussian distribution. So I have a smooth distribution of my quantum system, and all my measurements retain that Gaussian shape. They just squeeze it a little bit and displace it from side to side. So this is an example of a genuine continuous probing all the time, and having also a continuous degree of freedom that we actually probing. The B field itself is also continuous and varying with time. So the new thing is that the B field is varying. So I'm not trying to measure a constant parameter here. I'm trying to track the evolution of a time-dependent quantity. So what you see in the green is the true value, and what you see in the blue is actually the estimated value. So what we did was we assumed the same green field, but then we did a number of runs simulating the atomic dynamics, the measurement back action of the atomic dynamics. So it's all very, very intricate and complicated. But at the end, you get a best estimated value of the field for every experimental run. And if they all correspond to the same B field, then I can just take their mean value and their standard deviation as a measure for how good I am. So you can see there's a blue curve. There's also an area around it reflecting how much they scatter these values. So what you see is that we're doing a pretty good job, but it's also not perfect. In fact, our measurement scheme is pointing to what it thinks is the most likely value, but sometimes it's not the true one. It's not the true one because the green true value of the field sometimes chooses to monotonically drop for a while. That's not very likely. So it's not going to be your conservative guess for what it's going to be doing. So the blue curve will always be lacking behind that kind of behavior, because it really cannot believe that the B field is really going to do that. But of course, it does happen. So there's going to be a bias on our estimator. Every time the field is doing something unforeseen, then your estimator will be biased to not really expect that to happen. There's a certain time over which you have to accumulate data to get enough signal to noise, to get enough confidence that the value of B has changed. And then, of course, it has already changed again when you come to that conclusion. So this is why you see this lagging behind and also systematic error. But you can also see how the error is actually largest whenever B does crazy things. I mean, every time there's a spike in the green signal, there's an error, because you can really not guess that will occur. And every time there's a slope in the green one, there's an error, because you could really not guess that it would keep dropping or keep rising. Now, this is fun. This is the best you can do, except if you don't have to report at every given moment what you think at that time is the B field. If you're actually going to report afterwards, what was the most likely value of the B field as function of time, you can do better. This is shown here on the right, where it's the same green B field, but instead of just using the data up until time t to tell what is the value of that time, I use the entire data sequence from 0 to 2 milliseconds in this plot, and then I say I will use the whole data set to guess the value at any given moment of time. So you can see that the red curve is actually fluctuating less than the blue one does. It doesn't care about slopes in the green ones. It's actually nicely following when there's an increase. And the reason is that you are using data both before and after. So at any given moment in time on the right-hand plot, the estimate is based on both the prior data, but also the posterior data. And this can be formulated also in a Bayesian sense by something we call the past quantum state, but it's just a kind of extension of Born's rule, actually, for what is probabilities in quantum mechanics based on knowledge you acquired later than a given moment in time. You can still not explain the spikes, or you can still not guess the spikes, because later and earlier data can, of course, not know that the green one is going to do a crazy jump. But it shows at least the power and also improved power by doing a more refined data analysis. Now,
Klaus, could I ask you a question?
Absolutely.
So looking at what was done for the case on the left,
Yes.
this looks very similar to what I know of Scammon filter.
Yes.
Is
Thank
it
you very
actually
much.
doing the same thing, or?
Yes, the formalism is actually equivalent to Kalman filter with a small exception, and that is, of course, that we are using a quantum state for the atom. But the quantum state for the atoms is Gaussian. And because it's Gaussian, it's described by a covariance matrix, that is what is the variance of the Gaussian, and the displacement. And these are exactly the parameters in the Kalman filter theory. So there's a formal equivalence between this conditional quantum Gaussian state and the object that you're propagating in the Kalman filter. So this is exactly formally equivalent to Kalman filters with all the quantum things added on top. For example, that I cannot measure the atomic X quadrature without perturbing the Y quadrature to become anti-squeezed and stuff like that. So that's included in this formalism, something you normally don't care about in the classical Kalman filter. But the equations I propagate actually respect complementarity, and there are explicit terms that add noise to P if you measure X, or add noise to X if you measure P. But it's still exactly as you said, it has the same spirit. And in fact, in Kalman filter theory, you can also do a forward-backward analysis of data where you go in both directions. It has a name, I forgot it just right now off my head, and I'm not sitting in my own office, so I cannot see it on my desk. But so this is actually also part of the Kalman filter story. It's called smoothing. And it doesn't mean that you just take a pen and smooth the curve. It's actually a statistical analysis method that's called smoothing, using later and earlier data. So thank you very much. That was a very good question. Just because we had to try something else. And I think it's also an interesting thing to try on metrology. And this is work done with Mariam, a visiting student from Iran, where we, instead of using any of this quantum analysis, we actually trained a neural network on measurement data, noisy measurement data, and then we asked, can you train this neural network so that presented new measurement data you can guess what is the field. So the idea is that you teach or you feed the system with measurement data, then you let it guess what is the field, and then you make a mean squared error or some other measure of how bad it guesses, and then you make it sort of readjust all its neural connections in such a way that eventually it has minimized the error. So we do large training sets where we know the field. We know, of course, the measurement records. We haven't told it anything about underlying quantum mechanics. We haven't told it anything about master equations or quantum jumps or measurement back action. We just make a connection between the measurement record and the B field. And then eventually we give it a completely new B field. We synthesize a new B field, but we don't tell anybody. And then we give a measurement record and ask the computer to guess what is the field. And it performs equally well. And it actually performs equally well as my smoothing filter, because this network is also using the full measurement record to give the best estimate, which is the blue curve, for the time-dependent magnetic field. And the true one is the red dots. And you can see that it performs generally quite well. It performs generally quite well also when there's a slope in the data, but it doesn't do the spikes very well. That's, of course, exactly as it should be, because you don't have measurement data that can really tell you that the spike occurred, even if there is a spike in the data. So that was my last science slide. I want to jump to my conclusion. I had planned to finish a little bit earlier, but at least we still have 5 more minutes to finish here. So my conclusion, or maybe the take-home message, in quantum metrology, of course, you can do crazy and good things about initial squeeze state, preparing really good state that are super sensitive to dynamics. But you can also go this other way, where you just probe all the time and rather use the fact that the system dynamics is quenched, is modified by the measurement itself. And these quenches are exciting because they take you away from steady state, and systems are actually much more sensitive to Hamiltonians if they are not in eigenstate, if they are not in steady states, because that's where you can see how they relax. And it's exactly the Hamiltonian who governs relaxation of quantum systems. So it's a good idea to hammer on your system all the time, just to upset it a little bit and then watch the dynamics. And of course, you could do it with a real hammer, that is with a Hamiltonian, but you can also let the measurement process do it by itself, because the measurement back action is also disturbing the system. So there is this quantum system being conditioned on the outcome. And then when we do that, we have to, of course, have a theory. And I try to explain to you that this Bayesian theory just works. Quantum trajectory theory for free gives you also Bayesian filters. Okay. And the transient response, as I said, could tell us much more than steady state dependence on parameters. So that's really the feature in time dependent probing. We have the quantum Fischer information who sets a golden standard for how much information could be determined. It's fairly easy to calculate the quantum Fischer information. So therefore, I would always do it, because then I can benchmark whatever I do up against that quantum Fischer information, just to understand, am I a factor 10 away, am I a factor 2 away, how much should I think in terms of improving my scheme. Sometimes we can show that the Fischer information grows with t, that is, your error bar goes as 1 over square root of t, but sometimes we can find other dependencies. Systems who are ballistic in nature, undamped, will linearly evolve with time. And if you have an error bar which is a fixed size, then you will actually also have a 1 over time precision of your measurement. So it's a very interesting how to actually play with these scaling properties with time resources. Very similar to the discussion we have in many body systems. Does your fidelity or your Fischer information for measurement, does it go with the number of particles, or does it go with a higher power, the number of particles squared? People who do Schrödinger cat states and squeeze state for sensing, they improve on the n factor, and sometimes they can go towards this n squared. It's a little bit the same as the discussion of a Heisenberg limit versus standard quantum limit in sensing. Some of these laws about n and n squared, and also t and t squared, can be violently modified near phase transitions, where you can have certain parameters that change discontinuously or with a slope that's discontinuous, and then you get super sensitivity. But how can that actually be really managed in lab experiments? That's a good question. And then finally, we have this machine learning. That's a practical skill where we don't have to know anything. It's also something called compressed sensing, which has a little bit of the same feature to it, that it's a clever algorithmic way to actually compress your measurement data. There's lots of classical methods for processing that I think we have to learn how to integrate with the quantum systems. And if you start doing that, it's actually not very clear if you can retain the advantage of this Bayesian and at the same time use more phenomenological classical methods. So that's something we are really trying to work on in my group now, because we can see the potential of the quantum systems, but we can also see that the full quantum formalism cannot always be used. And then, of course, to your community, the QuSCo community, I mean, I think this is a super fascinating avenue for quantum control questions. I mean, every time I do a measurement, I have the potential either of acting on the system with a Hamiltonian that might make me even more sensitive to what's going to happen with the future measurement. Or I can also make adaptive measurements. So every time I get a measurement outcome, I choose to measure something else, a different observable. And that observable would contain more information than the one I would have measured otherwise. So this online processing, using your measurement record to guide what to do next is really a fantastic optimal control task. And with this 3:30, thank you very much for your attention.
Thank you very much for lecture. Are there any last question? No. Okay.
Yes, I have. Oh, okay.
Sorry.
No, I was just waiting if someone else had some other. Yeah. So I'm just okay. Maybe I'll just start video. It's easy. So okay. I had just a simple question of like, how often? So you do the measurements like periodically, like at some fixed intervals, or it's one should also be random, and then you would have different.
I imagine so. Of course, I'm a theorist, so I may not have a perfect model of how real experiments work, but I'm actually thinking about doing the measurements completely continuously in time. I imagine that my photon counter is on all the time. It's biased with some voltage. And then, of course, I know that every time there is a click, there might be a dead time in which I cannot see anything else. But if there is no click, then it's just the spectral bandwidth of the detector. I mean, what is the bandwidth of the detection that tells me on how fine a time scale it actually measures, right? So, I mean, for some experiments, you might say I detect every nanosecond. I measure every 10th of a nanosecond. I guess in other schemes, you would say maybe it's microsecond or millisecond time bins. But I don't have real time bins in mind. I think many detectors are working in this analog way that you know, what is it that happens in a photodiode? It's that you release some electron by the photoelectric effect, and then click, you see it being accelerated towards some electric detection device. And there's no periodic sequencing of that device. It's just sitting there. Then after every click, that avalanche has to die out so that you have new charges that are ready to be excited by the next photon pulse. And my theory does not take into account dead time. So in fact, we hope that we have so little dead time compared to the actual intervals between the clicks that I don't miss anything. And if you want to model, and we of course sometimes think a lot about that, if you want to model counting with a finite bandwidth detector and a detector with dead time, then you will have to model that in some way. It becomes non-Markovian. The trajectory theory doesn't work anymore. And we have one paper where we use the neural network actually to then learn how to extract the parameters. And that was in the complete absence of any other theory. So we benchmarked the network on a Markovian case, and then we applied it happily to the non-Markovian case after that.
Okay. And I have actually one more question, but if someone else wants to also go, can go before me. Anyone?
So maybe I'll ask one that it's in the same spirit, and then because it connects quite well. So it's about black photon count or dark photon count. Sorry.
Yes.
Yeah. This should be Markovian. So I don't know. Did you take it into account or?
We have done it for fun. So, and because just as you say, if that's the only problem you have, you can actually model that too. So I showed you the model where we're doing the counting in this waiting time distribution. And if you know there's a constant rate for dark counts, that is just going to modify that waiting time function in a, not a trivial way, but in a way we can calculate. So I'm sure I could have done that in a better way. But anyway, here we are, this red curve. And the red curve has exact zeros every now and then, because it's completely unlikely there would be a click at that time. The atom is back in its ground state during the Rabi oscillation. But of course, if you have dark counts, you don't go back to zero again, because there could be a click exactly at that moment in time, namely a dark one. So this red curve, I can calculate that in the presence of dark counts, and I can also model easily with my Bayesian theory that there's a certain chance that the click is not an atomic click, but a dark count click. So that we have actually done, yes, and that's a fun thing to do.
Thank you.
Okay, then I'll go ahead. My second question. So it was one of the initial slides where you talk about omega 0 being the true frequency, and then you take something higher and then something less.
Yes.
Yes, and then it's that orange, blue, and the black. Yes, this one. So the orange and blue are like symmetrically opposite.
Yes, and it's accident that it's symmetric, but it's not accident that the blue one goes down when the orange one goes up, because when you have a click, that's going to be more likely with the orange one. It's going to be less likely for the blue one. And since the total probability is conserved, when one goes up, typically the other one would have to go down. If you look a little bit later in the sequence around 15, you can see the orange one is increasing just a little bit, but the blue one is actually decreasing quite a lot in those particular events. But that's because the blue one is more comparing itself with the black one here, which has a high probability. And therefore, it's the blue one loses more and the black one is increasing. But so the Bayes rule is actually just giving very, very definite factors that have to be multiplied on the previous value. So at every step, the blue and the orange and the black curve are being multiplied with a given factor if you measure spin up, and another factor if you measure spin down. And the factor is different for the orange and the blue and the black. So that's why they go where they go. And the factor is the same for all the first 4 orange steps going up, and the same for the 4 blue steps going down. Then you renormalize, and then you get what we see in this figure.
Okay.
It's something our mind does all the time, of course. I mean, and you say, then this is not likely. A guy enters your office with a raincoat that's wet, and then you think, I guess it's raining outside. And if he enters without a raincoat, you think, oh, maybe it's dry weather outside. So and of course, it is the other way around. It's because it's raining that you put on the raincoat. So there's a probability going one way, but you can infer the other way, and that's what Bayes' rule is about.
Nice, thank you. And let's see if anyone else. I guess that is it. So I think we had 31 participants today, both from QuSCo, some from Jacob's research group, and then I think some from your research group, and some from Christiania's group as well, right? I think so. Yes, I can see a lot of other participants other than QuSCo as well. So that was really nice. Okay, if there are no more further questions, I would really thank you so much, Klaus, for this talk. It was really interesting. I think something new, at least compared to all the other. We haven't heard any similar talk like this, and it was sort of a very new perspective to quantum sensing in terms of doing measurements continuously, and I think that was really cool.
It was a pleasure. Thanks for having me. I mean, you should all be sitting now judging what's the probability that Trump wins tonight or Biden wins tonight. And I'm sure there's a Bayesian thing about that also. So then you can think back on this talk if you get too depressed about the outcome.
Yes. Matthias, did you want to say something? Or?
I just wanted to thank again Klaus, and to thank everybody for attending, and we will prepare the next QuSCo soon. Thank you very much, Klaus, again, and have a nice afternoon, everyone.
Perfect. Bye-bye.
Bye.
Bye-bye.